is dependent on this h. You must fix an integrable function such as h, then construct this function. Then mu is a real measure on this measurable space if we consider this f equal to r, and if we consider f equal to c, this is a complex measure, so that if we define mu by this function rho, this mu is a measure, real measure or complex measure. Okay, and we see this in the previous session. Now we can define notation hd mu. Suppose mu is a positive measure on a measurable space x and s, and h belong to L1 of mu. Then hd mu is the real or complex measure on this function space, on this measurable space, defined by this equality. hd mu is this mu. Okay, we denoted this mu by this notation. Okay, so that is equal to mu. Okay, in our notation, okay, by our notation, if for any for example, in S we define mu of e equal to the integral of f d mu on e, then we denoted this v by this notation, or in the book consider h instead of f and denoted h d mu. Okay, in this proposition we see some properties for complex measures. Let mu be a complex measure on this measurable space. Then we have these properties that we see these properties in positive measures, and these properties prove similarly and very easy. But we have the definition of total variation of measures. Please note that to this definition. Dear students, do you have my voice? Suppose nu is a complex measure on a measurable space X and S. The total variation measure is the function absolute value of nu from S to this interval defined by this equality. Absolute value of nu of E equal to this supremum, this summation for any natural number n, and this joint set in S such as E1, E2 up to the En. With this property, this union must be a subset of E. This is an important set function construct from a complex measure, and we see that this is a positive measure on S, okay, and it is called total variation of nu. This property is very easy, and we have this proposition. Suppose nu is a real measure on a measurable space X and S, then for any E in S we have total variation of E equal to this supremum of this summation, where A and B are disjoint set in S and this union be a subset of E, so that in real measure we can define this very simpler in complex case, okay, and we omitted this proof. Suppose mu is a positive measure on a measurable space X and S, and H belongs to H1, and the nu equal to this, then the total variation of this nu equal to this integral for every E in S, okay, so that in this proposition we see that proposition if X and S is a measurable space, and the space mu is a positive measure on S and F or H, for example, belong to L1 of mu. Then if for any E in S nu of E equal to this integral, then for any E in S, total variation of nu equal to this integral, okay? Equal to this integral, and this is very nice relation between total variation and absolute value of this measurable function, okay? We omitted these proofs to save time, and we have this proposition: total variation measure in a measure is a measure. Suppose nu is a complex measure on a measurable space x and s, then the total variation function is a positive measure on x and s, okay? Is a positive measure. And its proof is straightforward, but it is slightly long. For any complex measure on a measurable space x and s, the total variation function is a positive measure. So that we have this proposition 2, proposition if mu is a complex measure, then this is the total variation of mu is a positive measure. Positive measure, okay? And this is very important. Let me add it some new slide. Okay. Now, in the following, we see that the set of all complex measures consists a vector space and consists a norm space. At the first, we define addition and scalar multiplication of measures. Suppose x and s is a measurable space for complex measures nu and mu in this measurable space, and any alpha in our scalar field f. Define complex measures nu plus mu and alpha nu by these equalities. Nu plus mu of E equal to this, and alpha nu of E equal to alpha mu of E. You should verify that if nu and mu are complex measure, then this nu plus mu and alpha mu are complex measures too. And we have this definition. Suppose X and S is a measurable space, then MF of S denoted the vector space of real measures on this if F equal to real numbers, and denoted the vector space of complex measures on this measurable space if F equal to complex measure. Okay, so that this index refer to or F equal to R or C, real numbers or complex numbers. And then we have this definition, total variation norm of a complex measure. Suppose mu is a complex measure on a measurable space. The total variation norm of mu denoted by this and defined by this equality. The norm of mu equal to the total variation of X. Okay? Now we see that total variation is a norm. Suppose X and S is a measurable space, then for any mu in MF of S, this quantity is finite, and finally for any measurable space X and S, this space, the set of all measures on F is a Banach space, so that this is a vector space, and total variation norm is a norm actually in this space. So we have a norm space and a Banach space. Okay, this is very important, that this is a norm space. This vector space with this norm. Okay, this is a norm on MF of X. Okay, then we have decomposition theorem, and this is very important. Hahn decomposition. Suppose mu is a real measure on a measurable space X and S, then there exist sets A and B in S such that we have these properties. The union of A and B equal to X, and the intersection of A and B equal to empty set. Mu of E is non-negative for every E in S, such that E be a subset of A, and mu of E is negative for every E in S, that is a subset of B. Okay? For any measure on S, we can found two sets such as A and B in S with these properties. Okay? So that any real measure, so that please note that this nu is a real measure. Okay? Nu is a real measure. So we have let me write this for you. Hahn decomposition. Okay? If X and S is a real measure on S, then there exists A and B in S such that we have these three properties. We have these three properties. 1, 2, and 3. 1, X equal to A, the union of A and B, and this intersection equal to empty set. If E belong to S and be a subset of A, then sorry, I forget, X and S is a measurable space and mu be a X and S. If X and S is a measurable space, and nu from S to R is a measure on S. Okay, mu from S to R is a measure. Then there exists two sets such as A and B with these properties. For any subset of A in S, mu of E is positive, and for any element in S with this property, mu of E is negative or zero. Okay, dear students, do you have my voice? Do you have my voice? Wa alaikum assalam, Abdul Salam. Okay. Mu is a positive measure and S belongs to L1 is real value and define this measure. Okay, that we define so that mu of E equal to the integral of H on E. Then a Hahn decomposition of real measure nu is obtained by these two sets. A equal to the set of all x such as h of x is non-negative, and B equal to the set of all x such that h of x is non-positive or be negative, strictly less than 0. Okay, so that in this case, so in this proposition we can define A and B for any real measure. Know if H in L1 be real valued integrable function, we know that this is a real measure. Know for this real measure we have these two that have these three properties. Okay, now we have the definition of singular measures. Suppose nu and mu are complex or positive measures on a measurable space X and S. Then nu and mu are called singular with respect to each other, denoted by this notation: nu and mu are singular with respect together. Okay, if there exist two sets such as A and B by these properties, the union of A and B equal to X and the intersection of A and B equal to empty set, and for any E in S, nu of E equal to nu of E, the intersection of E and A, and mu of E equal to mu of intersection of E and B. If we have these properties, we say that mu and nu are singular with respect to each other. Okay, for example, If lambda is Lebesgue measure on sigma algebra of Borel subset of R, we can define two positive measures on this measurable space R with sigma algebra of Borel sets. Mu of E equal to this Lebesgue measure and mu of E equal to this for any E in B. Then we see that these two are singular with respect together, and mu lies on 0 infinity. Neither mu nor mu is singular with respect to lambda. It is note that these two are singular, but mu and mu are not singular with respect to lambda. Okay. So for this definition we must have two elements of S. In this example we can consider A equal to this set, for example, and B okay. Okay. You can consider, for example, A equal to 0 infinity and B equal to 0 or this. So minus infinity and 0. Minus infinity and 0. And B equal to 0 up to the infinity. Then we have these properties that, for example, R equal to this union and this intersection equal to empty set, and for any Borel set E is a Borel set and E is a subset of A. We see that by this definition. So for any E in S, we see that mu of E, this mu, okay? This mu. Not necessarily is a subset of E. Okay? Mu of E equal to mu of this intersection. It is very trivial. Because mu of E equal to the Lebesgue measure of by this definition, okay? We are in this example 9.29 minus infinity and 0. And mu of E, this intersection, equal to this intersect by this, and these two are the same. And similarly, for any Borel subset of real numbers, mu of E equal to mu of this intersection, so that we have these two properties. And another example, please read this example, these two examples, and write the proof of these two for me, okay? Please write the proof of these two examples for me. This example, let me write for now. Do you have my voice at now? Sorry. Let me repeat the Radon-Nikodym theorem. In the Radon-Nikodym theorem, we have this property. Suppose mu is a positive sigma finite measure on a measurable space X and S, and suppose mu is a complex measure on X and S, such that mu is absolutely continuous with respect to mu. Then there exists an H in L1 such that we have the mu equal to H d mu, or mu equal to H d mu. Okay, I saw that the Radon-Nikodym theorem shows that this example is very important, because in this example we see that if X and S is a measurable space and mu is a positive measure on S and H belong to L1, and mu equal to H d mu, or the mu equal to H d mu, then this mu is absolutely continuous with respect to mu. You can denote this measure with d mu or mu. Okay, then we have this property. Now Radon-Nikodym theorem proves the converse of this, or prove that any absolutely continuous with respect to mu have this property. For any absolutely continuous measure with respect to mu, there exists one H in L1 such that the mu equal to H d mu. And this is the definition of sigma finite measure as a, remember note for you, a measure mu on a sigma algebra S is called a sigma finite whenever there is a sequence such as an in S, such that we have these two properties. For each n, mu of an is finite and X must be equal to the union of this sequence. Okay, dear students, do you have any questions? Dear students, do you have any questions? Okay. We continue in the next session, inshallah. Thank you very much for your attention, and goodbye for now.